From home, okay. So first thing, there was a problem, a software problem with the submission because it took basically for everybody the standard group. So every new submission was rewriting the old submission. I'm not sure if your submission was involved because you were in a group by yourself, I think, right? You were in group A or group B, I don't remember.
Group A.
But group A, you see I have at least 3 group A submissions here.
Yeah.
So this is quite funny. I reopened the submission, check that your submission is in order. I will not delete your submission if it's in order. I'll give everybody else, for everybody where the document doesn't match the name, I'll just delete the document. And I'll give everybody else time until the 15th of June to update the submission. Now, before you do that, you have to be part of a group. I hope that wasn't necessary, but since it didn't work the other way, everybody will have to go to the group choice and be part of the group. Now, for groups, if you don't agree with with the guys in group B or group D, don't enter their group. And then create a new group by yourself if you are submitting alone. If you're submitting in 2, just agree on the group that you want to occupy and then use that group. Once you've done that, then go back to the draft and submit your draft there, as usual. And then I'll see them when I am back from the conference in 1.5 weeks. I will just check everybody. So next piece of information, I will not be here next week, as you know. There will be a talk by Ongpeng on PyBullet simulation for robotics, and then we're gonna pick up again the topic of Numpy, which we start today on the lecture after that. So that is going to be all for the administration. Let's move on to presentation. There we go. Which is the part on Numpy. So we start with the interesting stuff. So until now we've done threading, multiprocessing, a bit of general Python, a bit of class design, a bit of services and communication. Now we start with the actual numerical part of the course. So Numpy, TensorFlow, distributed computing. Numpy is the first topic in the first talk because it's the most used numerical library in Python, but I would just say just bar none in any language at the moment. And it is important because you have basic tools to do some mathematics in Python, but they're not efficient. And mostly if you start working with matrices or higher dimensional matrices, you cannot really do much without a specific library. In particular, the implementation of Numpy is efficient, and you can, in a very high level language like Python, you can do very optimized implementations with mathematical and matrix computation that you wouldn't be able to do without a library like this. Why? Well, because it's implemented in C. So behind the scene, when you create an object in Numpy and you operate on this object, the actual implementation of this operation is done in C and is optimized for speed. So you don't have to know about that. You don't have to know how it's implemented. It's just done for you, and you can use this particular features. And also there's incredible support for many aspects of mathematics, from statistics to computer vision to anything that you might think to do. There's probably somebody that has done it already for you. There's extra high-level libraries for machine learning, for example, SciPy, or for data analysis like Pandas, that are built on top of Numpy. So learning Numpy will give you the language for dealing with all these other extra libraries that build certain functionality on top of it. The language that is incredibly easy also because it's just built for simplicity, like most of the things in Python. It's intuitive. The way you address matrices are the way you write this in mathematical courses. So there's not much to learn. There's just to get used a bit with the conventions. and it's applied everywhere. I mean, if even if you do machine learning with TensorFlow later on, you'll see that when you create the data, when you manipulate the data in the beginning, you probably do it through Numpy, and then you bring in the data to your machine learning pipeline. So, yeah, I was talking already. Thinking about this again, optimized by performance, efficient handling of data set is also very important. There is exactly integration with a lot of libraries, as I said, and it's used everywhere. It's used in physics, in finance, in informatics, in simulations, in machine learning, in anything that you might think of. So, how do you use NumPy? Well, we've seen most of this already in some other examples, but basically you install it with pip, it's very easy, and then you import it with usually import NumPy as MP. Not necessary, but it's very useful for readability, because you'll find that everybody uses this syntax. So when you see a piece of code like this, even if it's without the import, you know right away that this is a NumPy array, right? So that's why people tend to use it, and that's why you should stick to this as well. So how do we create array in NumPy? Well, there are several ways to do it. The typical way, if you have a constant array, or if you want to initialize an array in a certain way, is to, somebody's ruined it, is to do basically an NumPy array and pass the constant as argument. This way you create a new object, which is nothing else than an array in memory, a C array in memory, on top of which you have the interface, the view, let's call it this way, of a NumPy array. So you can do operations on it using the NumPy library, but in the end, it's just a C array in memory. There are other very useful ways to create arrays that are particularly useful when you want to initialize quickly a new object of certain dimensions, for example, by using MP0s. And here you pass a shape. So a shape is a tuple that tells the library how many dimensions your array has, and we'll talk about multi-dimensions later, but in this case it's a matrix. It's a matrix with rows and columns, and in particular it has 3 rows and 3 columns, right? So that's basically what it is. So, and what it does create, it creates an empty 3x3 zero field array. Nothing particular. You can do the same with ones, NP ones. And it just creates, again, press the shape, it's always a tuple, and it creates then in this case, a 2x4 matrix filled with ones. These are floats. We'll see we can change this later on, but basically the standard thing that it does in 0.1 is it creates floats for you. You can also do some other interesting things. Sometimes you need to simulate like a loop, compute this parallelly instead of going through the elements of an array one by one. In this case, you can create a range like this, where you tell it from to where, and then you can say, but skip, every 2 elements. What's the step, right? In this case, we'll generate 0, 2, 4, 6, and 8, because 10 is always minus 10, less than or not less than equal, right? So this would create 0 to 9 if the step is 1, or if there is no step, otherwise it creates whatever it is less than 10. There is also these very interesting ways to create a sequence of increasing numbers, which is linspace. In this case, you give it beginning and end, and then you tell it how many elements you want. This is usually in float, but for example, if you have a particular simulation to do and you want to check several points along a certain dimension, you will do it with linspace. It's like, okay, build 10 buckets and then check the values at this particular values in the middle of buckets and see how the simulation does in this case. Well, then you do it linspace, you tell it beginning, end, and how many steps you want. So, as I said, there are several attributes beside the content. One is the shape, we already saw it. It's a tuple with the size of each dimension. So, again, in a multi-dimensional array, you can imagine it as a vector or a matrix, or a 3-dimensional cube, or a higher dimensional object in general, though, is just a list of number, right? Just a list of number where if you have, for example, rows, okay, the rows are basically indexing the beginning of a row, the beginning of the second row, the beginning of the third row, and so on. And then you have columns, and these are indexing the first number in the row, the second number in the row, the third number in the row, and so on. And then again, the first number in the second row, the first number in the third row, and so on. So you can do this game for higher dimensional arrays. You don't have to, I mean, I don't know about you, but I cannot imagine beyond 3 dimensions. And 4 dimensions is very hard. 5 is not, it's not possible at all. But everybody can imagine an array in the sense of a sequence of numbers. And then basically, let's say if you have 5 rows and 3 columns, that it means that you have 15 elements in the array. If then you add another 3 elements per column, so another, like a tower of number on top of each cell of the matrix, then you have 45 elements, right? And so on. So if you have the 2 dimension at the end, you have 90. So what you can think about is that, okay, this first index is indexing this 3 by 3 by 2, so 3 times 3 is 9, times 2 is 18. So it's the first 18 numbers. The first index of the 0 points at 0, the 1 points at 18, the 2 points at 36, right? And then you have, in here, you have 3 divisions. So the first index here, so if I take, for example, 0, 0, 1, 1, right? And I want to find the element that corresponds to these 4 indexes, I will take 0, then of these 3, you have 3 divisions. I'll take again the 0. The 1, though, will be 6 elements in front here, and then I take 2 elements, again 1, and that's the second element. That's what you get. So it's quite an easy way to visualize it. It's a singular sequence of elements of the size of your type, D type. So if it's a float, it's 32, 64, 128 bits. If it's an integer, it's 8, 16, or 32, depending on the size. In the end, you allocate 1 cell for each element of your tensor, multidimensional array, and then you use the index to find it. So what is interesting is in all this is that you can do very interesting mathematical operations on these objects. But again, so the shape tells you how many indexes and how big is the size of each index. The size tells you the count of the element, right? So in this case it was 90. The data type tells you how big is each data and how it's interpreted. So if it's a float 64, float 128. And then you have the number of dimensions or rank. You have to be careful. This is not the matrix rank, so the number of independent vectors in a matrix, right? This is the rank in terms of a tensor, which is the number of dimensions. So be careful when you use the rank, the nomenclature rank. So how do we access an element? Well, it's quite easy. If you want to access a precise element and you have, for example, a vector, you usually in math you underscore it by the index, right? Well, you use the square brackets here, and like you do in list in Python. They say the first element is 10, the third element is 30. First is 0, right? We count with 0, no Pascal. But if you have 2 indexes, well, you don't do this like you would do in lists, right? You don't do first 1 index, close parenthesis, second index, close parenthesis. You actually use a comma. You separate first index, second index by a comma. And then you can access that particular element. Right, that's simple. And now we come to actually what is particular of Python, which is different from list. You can use slices. Slices makes it possible for you to create a mask on top of an array. So if you say, I mean, this is my array 3 by 3, okay? And I can say I want the first row, right? Then you would say there would be a first row, right? 1, but every element in that first row, everything. If you want the first column, that would be a every row, so column 1. 0. What did I just say? We're not Pascal. 0, 0, okay? And the same goes for the second column. That would be A, column 1, right? So this works for basically selecting one particular dimension but leaving the other dimension free. But you can do more fancy things, like for example, you can limit a certain amount of elements. You can say, I want to take the first row, the first row, but only the first 2 elements, right? Then you would say A0, but let's limit it at 2. So anything that is lower than 2 is indexed in the second dimension, right? That would be this guy. You can do even more fancy thing, like you take the even rows, right? And the even rows would be like, in this case, A column, column, 2, column. And this would take basically this only, row, so this only row, right? The general syntax is basically start, stop, step. And then comma, next dimension. Start, stop, step. So if you have just a step, these 2 columns get contracted, and then you get column, column, step. And then you can take every third row, every third column, or you can do 1 column, column, step. That would take every third row, but starting from the second, and so on, right? So you can do fancy things, like for example, if you have an array and you say, I have 3 processes processing this data, and the first one looks at all the columns that are mod 3 equals 0. The second one looks at all the columns that are mod 3 equal 1. And the third process looks at all the rows again, not the column, that are mod 3 equal 2, right? And they never encounter each other because they are working on different sets of columns, of rows. But they can go on like that, like sequentially progress through the array without you having to divide the array in 3 big chunks from the beginning, right? So this is very useful for lots of things. What else? These are some fancy examples of how to limit and use it. Oh, and one more. So again, if you want to use an array and just don't touch a dimension and slice through the full dimension there, you just use the column. But there is a short end. If you just say, look, I want to take the first element or the second element here along the first dimension, and then don't mess with the rest of the dimension. Just use dot, dot, dot. And then it will take basically whatever else is left. Any questions on slicing? Clear? Very good. Let's move on. Boolean indexing. Now, this is quite interesting and very, very useful. You can create an array in Numpy by basically setting a condition. If you have a Numpy array and you say, well, Numpy array greater than 5, this will create an array with true and false. So every place where that array is greater than 5 is going to be true, and every place where it's false is going to be false. So for example, here you have basically true from 6 to 9, right? This and this are all true, the rest is all false, right? The fancy thing in this is that you can use this Boolean array to extract data from the original array, right? So you can use a matrix, not just the indexes, slices, but a matrix to select data from any other matrix. If the matrix has the same dimension, then we'll just select the elements that are true and not false, all right? And this will give you, in the end, just a list of elements, just a vector, one-dimensional array with the one that you've selected inside the matrix. This could be rank 3, this could be rank 4, that would be also rank 4. In the end, you just get a rank 1 vector with all the elements that fulfill that particular condition. Make sense? Right? So you'll find working on with Numpy that this construct here, Jesus Christ, where is it? This square brackets. This is very flexible. You can put a lot of things inside here, and it behaves. It basically interprets what you put inside with in the right way, right? You can do very fancy things. It's a lot more flexible than what you can do, for example, in TensorFlow, right? When you have some logic built in Numpy that uses fancy indexing like this, and you want to bring it to TensorFlow, most of the time you have to struggle because it doesn't work, and then you have to find ways that to reproduce this in TensorFlow. It's not easy. Basic arithmetics. I mean, TensorFlow, Numpy allows you to do basic math. Usually you would call this function np add, for example, a and b, right? And this will return an array that is the sum of a and b element-wise. What I mean by element-wise, it means that if you have an array like this, 1, 2, 3, 4, 5, 6, 7, 8, then the sum of the two arrays would be 6, 8, 10, 12. This would be the sum. So it's the sum of each element at each position, and it's the same shape of the array that you have above and below in the two basically operands of add. You can use this with normal plus operation. You can call directly the function np add. It's the same. There is absolutely no difference. I mean, there is a little bit of difference. This thing is an overloading of an operator in Python, so defined by NumPy. When it gets two NumPy arrays, basically the operator knows that it's been overloaded that way and calls this function. So if you use this, there is one passage more in the interpretation. But in the big scheme of things, when this is compiled, you don't care, right? It's if you do it 1 million times, it's just the initial calling of the function that you never care about that. The rest goes for minus, times, and divided. They just call different other different functions like np subtract, np multiply, and np divide. Okay, rather simple. Aggregation. Now, aggregation is something very useful because many times you have processes. For example, if you want to take an average, or if you want to take a weighted average of something, where you do some operational matrices and then you have to aggregate it. You have to aggregate along maybe some lines or some columns. And this is natively supported by NumPy. So let's say you want to get the grayscale of an image, right? Grayscale of an image, how you do with that? Well, basically you have to take the average of the red, green, and blue. Maybe you want to weight them differently. You want to do some operations on them, I don't know, to get a better grayscale. Once you've done that, you want to do it per pixel. So what you want to do is you want to take the average per pixel. Only in the, no, you don't want to get the average of the whole image because that's just one number. You want to get the average for each pixel of the 3 channels. Well, this is directly supported in NumPy. You just tell it axis 2, if your shape is width, height, and 3 RGB, then you say np mean value array / axis 2, and that's basically how you get that particular one. It supports sums, it supports means, it supports standard deviations, mean, max. So you can do a lot of things with this. Whenever you have an algorithm, translating it into a parallel argument for matrix is really very simple. And I think I just did the second slide. You can aggregate again, as I said, again, along an axis. What is important here is that you don't confuse what this axis means. So if you aggregate along an axis, it means that you keep the rest of the indexes stable, right? Let's say, I think this is a good example. If you have a 3-dimensional array like this, you see that this is 3-dimensional? Because it's 3 brackets at the beginning, right? That's the hint. If you want to count the rank of a constant, you just count the brackets for the first element. So if you are aggregating along the axis 0 and 1, what does survive? Which groups of numbers survive here? Anybody? I mean, the solution is down there, right? But we have 3 elements. Why do we have 3 elements in the end? What is the shape of this array? Can you see it? Let's start from the end. What is the dimension? Is the size of the last dimension of this array? Oops, sorry. Let me. There's an 18 here that goes there. So what's the size of the last dimension? 3. Why?
The first one is from 1 to 6 and 7 to 12.
So the first one, you mean this element. Oops, I have to turn the pen again on. This part is one row, right? This one is one column, sorry. This one is one row, right? One, two, 3 rows. 1, 2 columns, 3 elements. Right? So 1 to 6 is the first row. 1 to 3 is the first column, 4 to 6 is the second column. And for each column you have 3 elements, 1, 2, and 3. So you have the dimension is 3, the shape, 3, 2, 3. Does that make sense? So when you contract the first 2 indexes, when you sum over the first 2 indexes, what do? Which elements were you summing? Let's remove all this crap. What are you summing then? When I say sum along axis 0 and 1. You are changing the indexes. When you sum, you're changing the index to 0. So you're going through these 3 rows, and you're changing the second index. So it means you are moving along these columns. But you're not moving along the elements. They are fixed, right? You're keeping the last index. So if I build this sum axis 0, 1, sum axis 0 and 1, okay? And then I access the first element. Sorry. This is a number, right? And this element, this count, it's an index on the element here, on these 3 elements. So this one is the sum of 1, 4, 7, 10, 13, and 16. You see this? Does it make sense? Because I am fixing the third index. So if this is the original indexing, I am summing over this, but fixing this to 0. So it's 0 is always the first element in each row, in each column, right? And then I'm summing over all rows and all columns. Right? One way to think about this again, if you're doing aggregation along a particular axis, that you are contracting this axis. You're summing everything that is in this axis, but you're leaving the rest of the axis independent to change. So you can address the other axis, the third axis, and ask for the sum along, across the 0th element. So for all the 0th elements, or the first element, which would be 2 plus 8 plus 14 plus 5 plus 11 plus 17. Make sense? So you're going along these 3 elements at the end. Nodding, shaking your heads. Not really. Doesn't make sense.
I don't know why the output like this.
This one, well, I didn't do the sum. I don't remember, but I think that 1 plus 7 plus 13 plus 4 plus 10 plus 16 is 51. I assume. I would have to do it again. But the reason why it goes like that again is that I'm telling it to sum along the first and second dimension. Right? So let's suppose that there is no third dimension. Suppose that this is a matrix, okay? And it has 1, 2, 3, 4, 5, and 6. And I tell it sum along the first and second dimension. So everything, right? This would sum and result in 6 plus 11, 14, 15, that would be 21. Right? Right. So now I add another slice. Now I have 3 matrices, one on top of each other. And I tell it, sum along these 2 dimensions, but do it for the first slice. So S0, okay? And let's say on top of it, there is an S1, which is a different matrix, and it is like, 7 till 12, okay? The other 3 elements. So if I tell it, what is S0? So the sum over these 2 axes at the first layer, then it would be still 21. But the sum of the first layer, the second layer, so the layer 1, it would be 7 sum with 8, with 9, with 10, 11, and 12. So it would be a different sum, right? And so on and so forth. So you can imagine if I'm telling you to sum along the first and the second dimension, you basically are compressing this matrix into one number, but then you move to the second layer, you're doing the same with the second layer, and so on, right? But you keep that index alive. You keep that index alive, and you can use it to address the result. So if you at the beginning you had, in this case, a 3, 2, 3 shape, and you aggregate along these 2 dimensions, these dimensions become nothing, and you're left with just 3 numbers that are the last dimension that was left alive. Does it make more sense? All right. So this is aggregation. Very important, because you'll use it all the time, and you have to build an intuition for how this dimension combine and how to sum them and to build averages and so on. Because otherwise you'll find you put bugs in your code because you're thinking you're doing a sum and actually you're doing another sum. It happens a lot. All right. So, strict a bit. Oops. Okay. Broadcasting. Now, this is all easy and fun until you have all matrices of the same dimension. But sometimes you have to multiply a vector by a matrix. I don't know, let's say you have an image again, and you want to change the weights of the colors. So you have a vector, say, well, my red should be reduced by my red should be reduced to 0.5 what it was before, right? And I keep the green and blue as they were. And you want to multiply this vector by every pixel, right? How do you do that? Well, turns out there is a nice system in Numpy which is called broadcasting. So you can actually multiply a vector by a matrix, not as a vector and a matrix would usually be multiplied by summing across row and columns, but you can multiply this element-wise, for example, by adding 2 parentheses here and making this 3-dimensional array, right, of only 1 element across the first and the second dimension, and then multiplying the content of that 1 element across the 3rd dimension with the image that you have that has, many and many different pixels and row of pixels and so on. So every one of these elements would be multiplied by the same vector. Does it make sense? Right? You can do it also with scalars. It's even easier. So if you multiply 5 times this, or you want to halve all the values of the pixels, you just do 0.5 times this, and then you have halved all of the values of all the numbers. This is called broadcasting. The rules for broadcasting are very simple. Either the dimensions are equal, or one of them is 1. If one of them is 1, then it basically gets multiplied, basically reproduced n times until they're the same as the other matrix, and then it multiplies element-wise, like we did in the normal multiplication. If both are 1, well, then it's just a simplest case. But if one is different from the other, then one must be 1 so that we can do this. If one is 3 and the other is 4, it doesn't work. It gives you an error, right? Otherwise, it's very useful for all sorts of operations. In many cases, for example, if you want to create a grid, let's say, and you have a sequence is the easiest way to create a grid in Python or in TensorFlow actually as well. You create a sequence 1 to 5, let's say 2, 3, 4, 5, and then you create another sequence 1 to 5. When you want 2, 3, 4, and 5, what you want is to create, something like this: 0, 0, 0, 1, and so on, right? 5, 5. Well, what you can do is you can add a parenthesis here, add parentheses around each number here. So you have a row vector and a column vector with an extra dimension on the row vector. And then you can do broadcasting, basically on these two guys. And this will create a matrix, because it will expand the first dimension to 5 because the first one is 5 in the first dimension. The second dimension to 5 because the second one is 5 in the second dimension. So in this way you can do things like this by creating extra dimensions and moving them around. And anyway, this is very, very convenient and it's used everywhere. Reshaping. So sometimes you might think, well, it's nice and good to have 5 dimensions, but I really need 1 for this particular process, 2. Like you want to do a particular operation on the pixels that is not supported when you have 2 dimensions. You want all the pixels in a big list. What you can do is you can reshape. Let's say your image is 64 by 64 by 3. Okay, so 64 pixels wide, 64 pixel height, 3 channels, and you have a function that takes a list of pixels. So it's n by 3. That's the input that it gets. And you don't have access to change it. You can only do something with your data. What you can do is you can reshape this and say, reshape it please to 64 times 64 and 3. Now, these rows, basically, if this is your original image, the rows get put next to each other. And you have one big lines of pixels. And you can process it with your function, doing whatever transformation you do on the color map of the image, and then reshape it back to this shape, right? So this is also very convenient. It's used all over the place. And there are 2 simple shortcuts that you can use when you need to flatten the whole thing. The typical thing that you do, for example, in neural networks, when you have a convolutional neural network that has a very complex output, multidimensional output, the last layer is usually a fully connected network. I don't know if you've heard about this, but this is basically where every neuron speaks with every neuron. But what you do is usually first you flatten the whole thing and then you put the neural network on top, right? At the end. So flatten and ravel, opposite of unravel. It's do the same thing with one big difference. Flatten copies the data. So if you want to process the original matrix, but you want to process it by side effect, not returning a new matrix, you want to use ravel. If you're fine with copying the data and returning a new array, then you can use flatten. Be careful, because if you use flatten, you expect the original matrix to be changed. It won't. It will stay the same as before. This is best effort, though, as well as reshape is also best effort. Because if the array is non-contiguous, for example, if you have taken the even numbers from the array before with a mask, and then you try to ravel it into a single array, it won't work. It will copy the data because it has no possibility to keep the map to the original array. But it is a best effort case. So it's usually a good idea to test your function and not rely on side effects anyway, right? Any question on this? Reshaping, raveling, flattening? Good. Let's move on. It's a bit theoretical today, but we have to cover a bit of ground before we can do anything interesting. So VStack and HStack. VStack is very simple. You have 2 rows vector. You just stack them vertically. You create an array by putting all the rows one on top of each other. Right? HStack is the same. You have 2 column vectors. You put them next to each other. and you create an array. Same story. So if I apply this, you see these are column vectors, double parentheses, right? So these are column vectors because I have parentheses around each element, which means that it's one column. And this is one row. So nothing special. They are special cases of concatenate. So concatenate is a bit more involved because you can do concatenation along any axis, even the middle one. So when you do concatenation, again, keep an intuition of what's going on because it's important, because otherwise you get a mess. In this case, for example, we are concatenating along the second dimension, not the first, so not the rows, they're not just stacking rows, not the element one. So otherwise it would be 1, 2, 9, 10, right? If I was concatenating along the element wise, I would take this guy, then I would take this guy and put it next to it, right? This would be concatenating along the dimension 2. Instead, I'm concatenating along this dimension, along this index. So I'm jumping from this element to this element to this element to this element, right? And this is what's happened. 1, 2, 3, 4, 9, 10, 11, 12. Does it make sense? Right? If I were to concatenate along the 0 dimension, I would take this element, then this element, then this element, then this element. It would be basically the same geometry as it has right now, just more rows. It would be as basically putting a comma here and opening the array here and closing it here. It would be exactly the same thing, right? Make sense? So this is the concatenation. And basically, if you think about it, the V stack and H stack are just shorthands for concatenate along 0 axis and on the 1 axis. And they actually work also on higher dimensional matrices like that. Is it clear how this works? Good. Split. You can put stuff together, but we can also divide them. Split divides an array into subarrays. It creates a list of NP arrays. Doesn't create an NP array, doesn't create a new dimension NP array. It really create a list, a Python list of NP arrays, right? So how does it work? Well, you tell it along to split the array and how many elements you want. Usually it splits along the 0 dimension, so along the rows. In this case, 4 rows split into groups, you will split here, right? Just the first 2 rows and the second 2 rows, and that's what it does. But if you want to do it along the axis, different axis, for example, the columns, well, in this case, you have 3 columns. So I have passed, instead of 2, I have to pass 3, because anything else will fail and will give me an error. I mean, it has to have a multiple of that number in that dimension in order to be able to split it, right? So if I have 9 columns, I could have put 3 or 9, but definitely not 4. Does it make sense? And otherwise, it's just dividing, again, in this case, in, you see, 3 column vectors. It's keeping the structure, so it's not throwing away a dimension, but it's keeping the structure, it's just generating 3 column vectors. Here, it's clear why there is this clamor, this parenthesis here, this bracket. Make sense? All right. So now we go into real math. Dot and matmul. Dot and matmul are basically the same thing until you stay with 2-dimensional or 1-dimensional arrays. They basically do the dot product for vectors, they do the mat multiplication for arrays, the column by row multiplication for 2 matrices, or the vector by row or column by vector for, or sorry, row by vector or vector by column, if you do vector to matrix or matrix to vector. This is, whether you use dot or matmul doesn't change anything, it's just the same operation, right? You can see some examples here. I can multiply 2 matrices like this, I can multiply a vector on the right of the array, or a transpose vector times a matrix. And if you check, these are this is exactly this, and this is exactly this, right? So I've just reproduced the row by column of the first operation and the column by row of the second operation by using 5 and 7, so this column vector, and 1 and 2, so this row vector, right? Just to show you, it's exactly the same operation, it's just a different name. Whether you do a vector by matrix or matrix by matrix, it doesn't change anything. It's just different size of the matrix itself. Stuff gets interesting when you, I mean, this is clear, right? You don't have to spend more time on it. Stuff gets interesting when you do it in higher dimensions. So we see another way to create a matrix, random matrix. You pass it a shape, and this creates random values inside the shape. I don't care about what is inside. The only thing I do at the end is actually assert that something is similar, because there's always some rounding problems. If you, for example, compute the inverse, we'll see that later. If you compute the inverse of a matrix and multiply it back from the original matrix, you don't get 1, 0, 0, 1. You get 0.1 times 10 to the minus 16, or something like that, right? So you use this when you want to assert that something is equal, you use all close, and then it tells you that these two matrices are almost the same up to rounding error. So what I'm doing here, I am multiplying with dot product this matrix that is 2 rows, 2 columns, and 4 channels, like in an image, times this matrix that is 2 rows, 4 columns, and 5 channels. And what will happen is, if I do the matmul, let's start from the easiest one, the matmul will always multiply these two guys as if they were a matrix, and will match these two indexes. So it will take this like this, like if it were a batch. This is a good way to think about it. If you have a batch of matrices that you want to multiply, like a list, right? A list of matrix A1 and B1, and then A2 and B2. And you're interested in multiplying these two and then these two. But you're not interested in multiplying these two and these two, okay? You don't want to do that. You want to just multiply across the first index all the matrices that come along. So that's what matmul is for. It matches this initial index with this index, and then it does multiply these two matrices, multiplying across the last index of the first and the first index of the last, right? Rows against columns. So what do you expect the shape? Don't read the answer. What do you expect the shape when you multiply this batch of matrices against this batch of matrices, and you contract along this 4? What do you think will happen? So what will be the size of the first dimension, first of all? I have a 2 list of matrices, 2 elements per list, and I multiply the first of the first list with the first of the second list, and then the second of the first list with the second of the second list. How many results do I have in the end? Again, number of matrices that I have in the end, right? Just the number of matrices. We're not talking about the shape of the matrix here. Right? Let's write this down. So my first list, oops, dot pen. My list is A1, A2. Okay, this is the first dimension 2, so I have 2 matrices. The second list is also 2 matrices, is B1 and B2. Now I multiply this together, and I get A1 times B1. What did I write? I don't know. And then I have A2 times B2, right? Makes sense. Matrix multiplication of the first element with the first element, second element with the second element. How many elements do I have here? 2, right? So whenever you do math multiplication, this gets preserved up until the last 2 elements, up until the elements of the matrix itself gets preserved. If I had to arrays of arrays. So A00, A01, A10, A11. And I have another array with B00, B01, B10, and B11. And I want to multiply these two. Well, in the end, I would have, again, the same dimensions, but within each cell, I have A00 times B00 and so on, right? So in this case, I would have here not just 2, but I would have 2, 2, and I would need to have also 2 here, because otherwise I cannot match them, right? And the result will also still be 2, 2. So this gets always preserved. What happens to the rest? So this guy means to me that each of these matrices has 3 rows and 4 columns. And this one means that each of the other lists has 4 rows and 5 columns. Am I multiplying this right? Yeah. So now, if I match the columns with the rows and I sum over that, the matrix in the end, how will it be shaped? So you have 3 rows and 4 columns, right? Oops. You multiply by something that has 4 rows and 5 columns. So when you do matrix multiplication, what do? You do this guy times this, and you put it here. Then you do this times this, and you put it here. Then you do this times this, and you put it here. And then you do the same for the next column, and so on. So 5 times, right? I have 5 columns, so I have to do it 5 times. So the final shape is going to be 3, 5, right? So when I do matmul with multi-dimensional arrays, I basically have a stable first batch of index, which is going to be basically indexes my batch along as many dimensions that I have. And then in the end, I'm going to do matrix multiplication, conserving the first index of the first matrix, the last index of the last matrix. And in between, I sum, so they get annihilated, but they have to be the same, right? This is the condition. The rows of the first matrix must match the columns of the second, the columns of the first matrix must match the rows of the second matrix, otherwise I cannot do the operation. But in the end, what I get is, surprise, surprise, 2, 3, 5. 2, 3, 5. Okay, so dot product. Well, this is much more interesting because the dot product doesn't conserve anything. You get 2, 3, 2, 5. What is happening here is that the dot product is taking this guy and it's then taking these guys and then it's multiplying like this. A0 or A1, B1, A2, B2. And then it's saying, okay, let's index the first one and let's put it at the first index. So I have, the result is going to be AB, okay? 1 for this guy or 2 for this guy. And then let's take the second index and let's put it, also 1 or 2. So I have 4 possible combinations. I can multiply this with this, this with this, this with this, or this with this. And they end up, though, in this index and in this index, right? So what's happening is that it's also multiplying across here. But since this is also part of the indexing, because it's considering this a vector, you have first these 2 indexes, then you have this index, this gets contracted, then you have this index, and then you have this index left, right? It's not doing any matching. So if you want, it's basically doing a bit of magic by creating empty dimensions so that it can align them properly. I've done an example here, and I'll explain it to you then, so that it can match these like this: 2, 3, empty, 4, empty. Okay, where this is like basically an empty dimensions to do some multiplexing. Actually, let's put it 1. This is just an empty bracket. And on the bottom, you want empty, empty. Then you have 2. The 4 is contracted, and then you have 5. Right? In the end, you see the 4 gets contracted, so it goes away, and you get 2, 3, 2, 5. Does this make sense? What's going on here? So if you want to do something like this, well, you can use this trick by basically slicing the first matrix, taking all the dimensions, all the 3 dimensions, and then putting some MP new axis here. This helps you basically create the empty dimensions that you need, match them to the other empty dimensions that you create on the bottom, broadcast along these empty dimensions, and then since you have one empty dimensions over, you just do a squeeze. Squeeze removes any empty dimension. It's again a trick to remove dimensions that you don't need. Does this make sense? Again, matmul and dot is one of the things that confused me the most when I started Numpy, so that's why I'm spending some time on it. I also want to spend, since we have a bit of time, I also want to spend a few seconds explaining you another way to do this. Anybody has done tensor calculus here? Like, have you ever seen this formulation of the Maxwell equation? I'm not sure, because this guy, this formulation of the Maxwell equation, partial derivative across the indexes on the electromagnetic field formulated as F, anything like this? No? Okay, sorry. So anyway, this is a formalism that was invented by Einstein to create special relativity, general relativity, and so on. And it's the name of a very flexible way to treat multidimensional matrices, which is called Einstein sum. And it's called NP Ein sum. The way you use it is that you give it a formula. So formula, and then you give it 2 operands, the 2 tensor that you want to use it on, right? And the formula is written like this. You basically list the indexes, for example, let's say I, J, K, okay? And let's say I want to reproduce this matmon. So I want to have I, J, K for the first one. Then I want to contract the K with the second index on the second part, reproduce the I across this. So I'll say I, because this is the same, right? Same index. Then this one must be K because it gets contracted with the K from the first one. And then I have another index, which I don't have so far. So I call it help, okay? And then I say, what's the result that I want? The result that I want is I, because the first index gets preserved. Then I have J and L. And this is your formula. And you can write whatever you want here. You can contract indexes, you can leave them alone, you can have, several index contracted in different places. It's very flexible. It's a lot more flexible than matmul. A little bit less efficient. It's not as optimized, of course, because it's so flexible. But it's when you have to prototype something, I find a lot easier to work with this because you can basically program it as you want and not try to get your head around how to reshape, concatenate, modify the tensors so that it goes through matmul or to dot product, right? This is a lot easier. And again, you can put as many indexes as you want and contract as many as you want. You have to do a bit of math to be careful that it's either contracted or passed on, right? So if you have an index here like I, then it's passed on. But if you have KK and not K here, then it's contracted. Then it's summed along that dimension. That's the basic rule. If you have it only here, so what you shouldn't do is have like the J here, but no J here. I mean, what happens with this J? It's not summed with anything and it's not passed along. So what does it mean? So this won't work. Does it make sense what I'm talking about here? Right? So if you sum indexes, it's just on the first part of the formula, but not on the second part. if you match element-wise on this particular dimension, then you write the same index here, and on the result. It means that the first element here and the first element here get combined to get the first element of the result. But if you write just an index here, no matching index here, and no matching index in the result, what's happening with this index? Nobody knows. You have 2 elements here in the second dimension, but I don't have an index here to match them to, and I don't have an index here to match them to for summing. So this will give an error, right? So this is Einstein's sum. You'll see it all over the place. It's quite useful. So if you do this nice operation with the squeeze and the new axis, and then you assert that this is the same, it's actually the same. So it's not just a chance that you get the same results. Determinant and inverse. So you all know what the determinant is, right? And you can very well compute it with linalge package. You can compute the determinant, the inverse of a matrix, or anything else. It's quite useful. Of course, the inverse won't work if the determinant is 0, but I mean, it's just very fast. What is more interesting of the linalge package is the possibility to compute eigenvalues and eigenvectors. You came across this stuff? Eigenvalues, eigenvectors, right? Okay. Gives you an example of what they're good for, anything they're good for, anything used eigenvalues and eigenvectors for.
Conscious theory.
Sorry?
Conscious theory.
Mm-hmm. So, I mean, they're used everywhere, right? And so it's quite simple again to get. You just call eig, and you get right away both the eigenvalues and the eigenvectors. Quite convenient. That's it for the presentation, which means we can look at one example, which is doing something a bit more interesting. All right, so here I have with a little bit of an example on image processing using Numpy. It's not the most efficient because it's non-parallel on the GPU. It's just implemented very efficiently on the CPU. So if you want to do usually image processing, you would do it on the GPU with something like TensorFlow. But anyway, it's good enough for what we have to do. And usually it's good enough unless you have really big images and big batches of those images. So we load the images. You have seen this before. I basically define a batch size down here, 3. I define where my images are, and I go through the range, and I use pillow to open this folder and this particular image. These are images of birds. We scaled it to 64 times 64 times 3. I append this to a list, and I divide by 255 because the images are usually formatted 0 to 155, but I want to have them formatted in float 0 to 1 because of the math that I want to do with this, right? And then what I do, I return NP arrays images. Now this is something that you find also a lot. First, I define a list because I don't know how much stuff I have. I load all my images into one list, and then I convert it into an NumPy array, only at the end, right? So what I want to do with this is process them step by step, and do some transformation. This is also very typical. If you do in machine learning, you probably do augmentation. So you want to rotate the view, you want to add white noise, you want to do all kind of stuff. In this case, I'm going to do a gamma correction by exponentiating the value in the RGB times the gamma factor. Right? You've seen this before. It's just the standard. When you see this in PowerPoint, in Photoshop or GIMP or any similar program, you basically have this curve that you bring up and down that is a parabol, and then you end up with something like this. But not a parabol, it's a power, and you end up with something like this. And then I'm going to use a rotational matrix on the RGB vector. I mean, a vector, RGB, it's 3 pixels, it's 3 values, so it's a vector, right? So I can do rotations. And I can implement a rotation across red and green to basically rotate by 45 degrees everything between red and green. So red will become a mix of red and green will become a mix of red and green. A perfect mix of red and green will become green. The perfect mix of green and red on the negative scale will become red. It doesn't make sense, but anyway, you get something like that. So do this, and then, I mean, for the sake of the argument, I did reshaping here to compress everything in one single row across the batch instead of row and column. And this -1 is very interesting as well. So we saw it before, you can reshape by giving the number of pixels, row times columns, but I can just put a -1. And this will collect any leftover elements count. So if my shape is, I'm already using this. If my shape is 3, 64, 64, 3, like it is now, 3 images, 64 width, 64 height, and 3 pixels. Where if I say reshape it into 3 -1, 3, what will happen is that it will take the size, which is this times this times this times this, which is the total size, okay? It will divide it by whatever is here. So divided by 3, divided by 3, and what's left, it will be allocated to the -1. So it will do the math for me. You can't put 2 -1, of course, because then it's not defined. But you can use 1, and then it will automatically work. Then I apply with matmul the rotation, right? And by using the transpose on the right, and then I transform it back. This is also another technique you'll see a lot. You save the shape of the original element, and then you reshape it to the original shape, right? So you don't use a constant for the shapes. You don't use you don't hardcode it. You always save whatever you had. You do the reshaping, do your math, and then use that particular save shape to go back to that, and then return the transform image. Now we call this dot image, transform image, and then we just plot it in a 6x4 array. This is matplotlib. I think I used that before, but I'm going to go on about matplotlib a bit more next time, together with other stuff from Numpy. But I think it's very important to get used to matplotlib. It's a very useful tool. You can do 3D plots, you can do 2D plots, you can do images, anything you want basically. But anyway, in any case, in this case, I just create a figure with a certain shape, and then I allocate here where my stuff goes, right? So first row, I have the original images, and the second row, I have the transformed images. So if we run this, we get this nice thing. With the original birds and the darker birds, because I decreased the level by using a higher power than 1 power, right? Makes sense? If the gamma curve is like this, it means that, you know, a 0.5 has been reduced to 0.2, for example, right? Range in value for the red channel, for the blue channel, and so on. So greater than 1 gamma is going to look like this. So it's darker, and then I rotated green and red, so you have these strange effects on the colors. And you can play around with these kind of things, and you know, for example, you can ignore the gamma correction, the U rotation, just run it again, and then you see it's just it's now just darker. Or you can ignore the gamma correction, but do the U rotation, and then it just goes bright but corrected in the U. So I mean, this is some game that we played, but this is very useful when you have large image data sets, for example, and you want to implement some augmentation. If you're doing machine learning, you'll find out that it's very hard to get data. So whenever you get data, you try to use it anywhere you can. So you start saying, okay, but what if I rotate this object? If I rotate the image like 90 degrees, it's a new image, right? It's a new data point because the neural network doesn't know how to rotate things. So I can rotate it and get away and get a new data point. Then I can change the hue to something not as bad as this, but still realistic, or change the brightness, or change the contrast, or blur it. And then you keep doing this, and you get more data points. And you get more independent ways to, at least partially independent ways to train your machine learning machine. So that's why we do this. Okay, I guess we are done for today, at least with the standard stuff. So if there is anything that you wanted to discuss, also project-wise, I will be very glad to do it now, because then this week I'm not here. So any question related to the class or to the project, it's a good time to discuss it.